The book begins with a philosophical essay on what is a force. And in this case, I think it's a useful exercise. Um, when we get to what is energy, I will make fun of it. I think it's kind of vacuous. But so usually people respond, and it's not a terrible thing, that a force is a push or a pull. But that rather implies contact. Um, and so a better uh, definition of force is that it is that which causes acceleration. That I think that's very useful way to think about force and the nature of force. That whenever you see an acceleration, there must have been a force that caused it, and whenever there is a force acting, there will be an acceleration as a result of it. But sometimes there are forces present and there is no acceleration. In the case of equilibrium, that if there are multiple forces present and they are canceling one another out, then they would not cause acceleration, but perhaps we could say force is that which has the potential to cause acceleration. And there I think we have captured what we mean by force. Um, I just add on in the spirit of trivia that in particle physics, a force represents the exchange of a virtual boson. Um, that in the case of electrical or magnetic force, it's a photon that gets exchanged. In the case of a weak nuclear, it's a W or a Z boson, and in the case of strong nuclear force, it's a gluon that's exchanged. But that is not the stuff we are dealing with. Now, Newton has these three laws of motion. I expect you to know them from last year, and I expect you to remember them and continue to know them. That Newton's first, and this is an opportunity for you to show yourself that you know it. You could say it to yourself before I drag it onto the screen, that objects continue in motion, continue in the same motion unless acted upon by a force. That this you need to respect as a very profound and non-intuitive understanding of the universe that Galileo gave us. Newton gets to put his name on it. There may have even been people before Galileo. Look at this illustration from a pre-Newtonian time. And the idea was that you couldn't have motion without a force. The idea of having motion in the absence of force was nonsense. That things sit still because nobody's pushed them. And if somebody pushes them, then that's why they're moving. But the understanding was that this cannon pushes the cannonball, but what's pushing the cannonball when it gets away from the cannon? And this pre-Newtonian understanding was that the cannonball was given something called impetus, which is sort of like rocket fuel. And that is what continued to do the unnatural thing of making it move, continue to push it until all of the impetus was used up, and then it stopped moving and just falls straight down. That is, of course, wrong. That the true understanding would be that captured by Newton's first, that in fact the path of the cannonball is one which continues with unchanging velocity horizontally, because if we ignore air resistance, there's no force acting horizontally, and continues with accelerated motion vertically, because there is this force called gravity acting vertically. And in fact, the path is a parabola as a consequence of those two non-accelerated and accelerated motions. But Newton's first. Newton's second. And again, I hope you can recall that before I drag it onto the screen. As Newton stated it, It was that force is proportional to the rate of change in momentum. That we will deal with this treatment that force is equal to the derivative of momentum with respect to time later, not now. What I would have expected you to have recalled is that force is equal to mass times acceleration. Again, that notion that force is that agent which results in acceleration. I don't like this, and indeed I will take points off of you if you write that, and I'm looking for the formula that you're working with. You need to instead write this, because it captures an important understanding that the acceleration that you get is not due to the force, but due to the net force, the sum of all of the forces acting on this body, this mass. So we need to figure out what all the forces acting on the body are, and that, of course, is a free body diagram, which you may object to. I know that once upon a time Mr. Houghton objected to them. He thought they were Mickey Mouse, silly little busy things that textbook writers needed. But they're not. They are so rich. And if you leave this course with that feeling about free bodies, I have failed. You need to make free bodies. You are given points for the free bodies that you make. That the process of a free body starts with first identifying the body, and that is not a empty task. It is very significant that you be very clear about what your body is, and if as you do the problem you find it is not working for you, you probably need to go back and again be very intentional about what you should treat as the body. And then you need to capture all the forces acting on the body as vectors away from the body. Don't try to capture all of the forces, just all the forces acting on the body that you have identified. And then, this is not part of a traditional free body. I think it is so important you need to indicate the acceleration. And indeed, the acceleration is a vector, and that could be confused with these force vectors that you were drawing. So you need to very clearly put it off to the side so it's not confused with the force vectors. And then finally, having identified all the forces and the acceleration, you then work with them. You add up all the forces. You add up all the forces in the direction of the acceleration, and that results in the acceleration. And then you add up all the forces perpendicular to the acceleration, and that results in the perpendicular acceleration, which is 0. Okay, we'll do an example of that. But meanwhile, we need to come back to talk about forces. And the first special force we're going to deal with is weight. And it is very important, and I hope you got this last year, that weight is not the same thing as mass. In the presence of a gravitational field, there is a relationship between them, but they are not the same. That mass is measured in kilograms. Weight is a force. It is measured in newtons. So please be very clear about that distinction. And what they tell you in the book is that force, that gravitational force is not the same thing as weight. That is unfortunate. That is perhaps true, but I find that unfortunate. You are going to hear me repeatedly make a free body, and I'll indicate the downward force on the body, the force from gravity acting on the body, and I will call it weight. But I shouldn't. I should call it F sub g. It is a force that results because the body you have identified has mass, and there is some second body that also has mass, and as a consequence of those two masses, there is a force between them. Weight, in contrast, is defined by your book as the force that you have to apply to keep the body from falling. That is, how hard do you push up to keep this gravitational force from causing an acceleration downward? So if you stand on a bathroom scale and it tells you how hard it's pushing up to keep you there, then that is indeed your weight. Okay, that's a subtlety that I need to struggle with, and I may not. But then the book makes a mistake. They say that at the Earth's surface, weight and the force due to gravity are the same. They result in no acceleration. This is equation 510 in the book on page 95. It's wrong. That is such a thrill for me to read the text and realize that I know they have made a mistake. And it is so scholastic of me to be reading critically and to be asking myself, do I agree with that statement? And I expect you to read the book that way also. And I most certainly expect you to listen to these lectures that way. And where you think I have made a mistake, you need to struggle with that, and you need to come into class, and you need to say, I think we need to talk more about that thing. You don't have to say I made a mistake for fear that you feel embarrassed when you find out I didn't. But you do need to be intellectually engaged, that you are not just taking at face value what I say, but saying, do I agree with that? And there comes the intellectual growth for you. Then the book has this set aside with a green hand pointing at it, indicating profundity and importance, that a weight is equal to F sub g. But they're wrong. That objects on the Earth are rotating. That there is no acceleration. Objects at the surface of the Earth, with the exception of those at the north and south poles, are going in circles. And when you go in circles, you accelerate towards the center of the circle. And that means that there is not zero net force. If there is zero net acceleration, they are wrong. Indeed, that acceleration depends upon the radius of the circle you're moving in and the velocity. You may or may not recall it's equal to v squared over r. So if you go to the radius of the equator and consider the rate at which the Earth is turning at that point, it comes out that the acceleration due to gravity is a little bit more than 0.3 of a meter per second, which is not at all insignificant when you have the acceleration due to gravity of 9.8. So I think the book is just wrong, although I will use W when I ought to be using FG. Shame on me. Okay, so 3 special forces are discussed in the book, and more will be added on later, like that centripetal force we were talking about. But the first was weight, which I think we have established how we're going to deal with that. The next 2 were normal and tension. That if you have a book on a table, then this weight force is going to pull the book down. Wait a minute, Mr. Houghton, that's supposed to be F sub g. I'm going to call it weight. But because the book is pulled down by gravity, it tries to go crashing through the table. And the atoms which make up the table say, yo, wait a minute, we're not stepping aside for you. And because of the electrical forces holding the atoms together, they say, we're not going to move. And so in reaction to the weight force, there is this normal force. And the word normal means perpendicular. It always acts perpendicular. And it is a reaction to this weight. And it says, no, you are not going through the table. Similar to tension to normal is tension. Again, there is some ogre who comes along and tries to tear this rope apart, pulls outward on the rope, and again the atoms say, wait a minute, we've got a force holding us together, we're not going apart. And so in reaction to that outward force, there is an inward force which is the same throughout the rope, holding all the atoms together, saying we're not going further apart because we got the electrical force to do that. It is drawn as arrows going in at the ends, but it acts throughout. A fourth special force, which you will work with but is not mentioned in the book, is compression. If you have a rigid object and you try to squash it, exactly the opposite. Here we try to stretch this, pull it apart. Here we try to squash it, that is, to move the atoms closer to one another. And again, there is an electrical force that says, no, we're not going any closer together. And so because of that, there is a reaction force that holds all the atoms at the same distance apart. We draw it as vectors at the end of the object going outward, and that's called the compression force. Okay, now an application, especially an application of free body, that you might feel like is such a simple problem you don't need a free body to do it. And I'm going to show you that you're wrong. So the problem is that you've got 20 newtons acting on this 4 kilogram object, which is right next to a 6 kilogram object. There is no friction between these two objects and the table, and we want to know the acceleration of object A. Well, 20 newtons acting on the 4 kilograms, that means that there ought to be an acceleration of 5 meters per second squared. And you get the problem wrong. And the reason you got the problem wrong is you didn't appreciate all the forces that were there. And that's why you need to do a free body. That also on object A, there was, in addition to the 20 Newton push, there was the gravitational force of the Earth pulling it down, and there was the normal force from the surface pushing up. Those two are in equilibrium, so there is no acceleration up and down. The acceleration is going to be to the right, but this is not complete. As regards the forces on this object, there is also a force from object B. That object A tries to push its way through object B, which is in the way, and object B has this reaction normal force that says no. And if we did not include that force, we would get the problem wrong. Now, with the problem done correctly, I will add up all the forces. And I really ought to distinguish that I'm adding up all the forces parallel. And then perhaps over here adding up all the forces perpendicular. And now I can put in here that the forces acting parallel are those 20 newtons, and the normal force from B acting on a mat. The object I have chosen, my body, has 4 kilograms, and there's the acceleration I want to know. But I've got the normal. It turns out I would get no information out of adding up the perpendicular forces to get the fact that there is 0 perpendicular acceleration. What I want to do is do another free body on B, which would have a force from object A. That would be a normal force from object A. It also would have a weight and a normal from the surface. It has no force going backwards. Who would provide that? There is no friction here. So all the forces acting parallel to object B are going to be just that, what I referred to as the normal force here. It was this force, but it's exactly the same size as that force. That's an action-reaction pair. And then I need to also recognize that the parallel acceleration of object B is going to be the same as the parallel acceleration of object A, so I can use those two as simultaneous. And then I have two equations with two simultaneous equations with two variables, and I can solve for A, which was the purpose of this problem. I point out that you could do it much more easily by choosing as your body object A and B together. And then the only force acting parallel on object A and B together would have been the 20 newtons. There was no friction force going backwards. These two, the red ones that I drew here, were an internal force, and they cancel out as an object action-reaction pair. But at any rate, now my body that I chose had a mass of 10, and I can get its acceleration, and then I could reason that the acceleration of AB combined is going to be the same as the acceleration of A, and be done with the problem. And that concludes our lecture.